Hi everyone! In this video, we will learn how to compute a mixture design with constraints leading to pseudocomponents with our software kit. Let's start off with this example, an optimization of an ACE fruit juice recipe. This is a commercial formulation to be optimized. In this example, the water amount has been taken constant, so these are the three ratios. Orange juice at 66.7% and the carrot juice and lemon juice at 16.7%. Starting from this recipe, bilateral constraints have been set for each element. This one for orange juice, this one for the carrot juice, and this one for the lemon juice. So, by setting these three bilateral constraints, we obtain this regular experimental domain. And therefore, we can work with pseudocomponents. Let's have a look at them. Pseudocomponent 1, pseudocomponent 2, and pseudocomponent 3. So, within this experimental domain, we can set our experimental matrix composed by 7 experiments, and from these, we can get the postulated model, including the linear, quadratic, and cubic terms. Now, let's go to the dataset. As always, you can find the datasets in the working directory in the cat folders. I have already opened the DOE file. You have to go to the 9D spreadsheet ACE. So here we can see the experimental matrix composed by 7 experiments. Every product was judged by 4 judges of the panel test. R, P, M, and D, and the results have been converted into the scale within a maximum of 100. In this video, the average score will be used to calculate the model. So basically, I'm going to import the matrix into CAD with the final average score. Okay, now we can start CAD. Here we have the matrix ACE already loaded by using the copy and paste option, since it's a very small dataset. Here we have our 7 experiments with the final panel average score. Now we go to the menu Multilinear Regression Design of Experiments. We click on it, and to compute the model, we go to the model computation as always. We click on Mixture. Now in this dialog box, we have to input the matrix name as always, which is already here. ACE. The rows to be selected, all. The X variables, so we input 1 to 3 by using the semicolon, and the Y variable, our response. As we have seen in the previous video, not every voice has the star code. So we can compute the model before performing any experiments to check whether the matrix is compatible with the postulated model. In this case, we have our response, so we type in 4, which is the 4th column of our dataset. Here we must specify whether the quadratic and cubic terms, beyond the linear ones, must be included in the model. In this case, we select both. We click on OK. This dialog box defines the higher terms of the model. So, if not all the terms are required, then input 0 in the corresponding cell of the matrix by clicking it and typing in 0. In this case, we are interested in all the terms, so we leave the ones and we hit OK. Then we have the dialog box, which allows us to choose how to estimate the experimental variance. In this case, we go for the residuals. Here we have all the numerical outputs with the dispersion matrix and the coefficients. In this case, we can't check the diagnostic since we have only 7 experiments available to estimate 7 coefficients. So we don't have any degrees of freedom. Anyway, we can still get the leverage plot, and to do this, we go to MLR-DoE again, and we go to leverage surface, and here we have to select mixture no constraints, so without any constraints, since we're dealing with pseudocomponents. We click on it and here we get our plot. So this is the leverage with the corresponding color scale. And, very important, as I showed you in the previous video about the experimental design, according to the leverage you can get the semi-amplitude of the confidence interval in every point of the experimental domain. But as we know, in this case, we can't calculate it since we don't have degrees of freedom. Despite this, let's see how we can get this. We go just below leverage surface, we click on confidence interval surface, and again we have to select mixture with no constraints. We click on it. As always, we are asked how to estimate the experimental variance. So we select residuals again, we click on OK, and obviously CAT reminds us that we don't have degrees of freedom. We click OK. Now let's have a look at the response surface. So we go to MLR-DoE and go to response surface. Again, we need to select mixture with no constraints. And here we get the response surface with a color scale at its side. We can notice very well the trend in our response in the experimental domain. So in this region we have the highest score for the panel test, and in this region the lowest one. Alright, now let's have a closer look at it. We are roughly interested in the left region, so let's consider this point, and from this we can get the pseudocomponents coordinates. 60% of PC1, 40% of PC2, and 0% of PC3. By using these coordinates, we actually can predict the response at this point within the experimental domain. To do this, we need to call the function prediction in the MLR-DoE menu. But first, we have to import the coordinates of our point, a set of x values, which in this case have been already loaded with the name OPT. So we type in the console OPT, we enter, and here we have the x values within the pseudocomponents domain. Now we go to prediction MLR-DoE. We have to select mixture. The dialog box, as always, requires the matrix name with the experiments to be predicted. So in this case we type in OPT. Then rows to be selected are rows. X variables again 1 to 3. And in this case we don't have our response, so we leave none on the Y variable voice. We hit OK, and now we can see the response prediction on the console with the corresponding leverage. At this point, in summary, thanks to the experimental design, we got our optimal coordinates within the pseudocomponents domain. And now we have to convert them to the actual values of the components. Basically how much orange, carrot and lemon juice is needed. So again here we have our domain. And now let's see in the actual components domain. So the question that arises is, what are the real components amounts needed? Geometrically it's quite simple. And actually we could make an accurate guess, but let's see how to get them mathematically. Basically, we just have to multiply each coordinate of our optimal point by the composition of its pseudocomponent. And here we can see the operations. After that, we just have to make the sum of the results and we get the component's coordinates. Finally, here we have the component amounts. So 72% of orange juice, 18% of carrot juice, and 10% of lemon juice. And here we compare again the two domains. So we've come to the end of the video. I hope you've enjoyed it and see you at the next one. Don't forget to subscribe and to like the video. Bye!